So in today's session, we will be understanding what are the design parameters and design equations that will be helpful for us to design a MEMS cantilever beam. Once we understand how to design and simulate MEMS cantilever beam, MEMS design becomes little easier because by then we would have known few nuances that is very helpful for designing other MEMS devices. So we are starting with MEMS cantilever beam because most of us are in the beginning stage, and it is really important for us to understand how exactly the design flow is carried out in MEMS design. So starting with MEMS cantilever beam gives us a fair idea of entering into the MEMS world. So having said that, first let's understand what exactly is MEMS cantilever beam. As I explained in the session 1, MEMS cantilever beam is a beam. It is a rectangular shaped beam of any material. It can be silicon nitride, material which has flexibility to move, right? When we apply a pressure, the material has to move. So we choose a material which has good flexibility for the applied pressure. And then what we do, we shape the material either in rectangular shape or usually it will be rectangular. Cantilever beams are rectangularly shaped. And then what we do, we fix one end of the cantilever beam and we apply pressure or force on the other end where the cantilever beam is free to move. So on the application of pressure, the cantilever beam moves away from its origin. That means it deflects, right? So due to this deflection, the deflection will be distributed over the body of the cantilever beam. But the area near the fixed constraint, what happens is that the body wants to move, but it's not able to move because it is fixed, right? It is fixed towards it is fixed. It cannot move. So at this condition, what happens is there is a stress generated around the region where it is fixed. So whenever we design a MEMS cantilever beam, we have to know that fixed region will have a stress generated. And what is the maximum stress that is being generated by the cantilever beam is very useful because variation in the stress can also be used as the steady parameter. So there are two steady parameters. One is the change in the stress near the fixed region of the cantilever beam. Another is the deflection of the tip from the origin, right? It deflects when the pressure is applied. When the pressure is removed, the cantilever beam free end will come back to its original space. Sorry. So this is the physics of cantilever beam. The cantilever beams are used in multiple applications. One such applications is our AFM, atomic force microscopy. It is used for imaging the surface. Okay, whenever we have a sample, what is the surface, how the material is deposited, can be examined using AFM, that is our atomic force microscopy. And atomic force microscopy uses cantilever beam to do the surface morphology. So that is one application of cantilever beam. Cantilever beams are also used in biomedical applications to detect the antigens and analytes. So it also finds application in medical domain, and there are many such applications of cantilever beam. So biosensors, cantilevers are used to detect the blood groups, blood diseases, where the stress level of the cantilever beam varies with blood cells, different blood cells. So there also we can use our cantilever beam. So plenty applications are there for MEMS cantilever beam. What are the dimensions that is required to understand in cantilever beam is, as I explained, it is a rectangularly shaped device. So rectangle as length, width, and thickness. So as you optimize the dimensions, there are different analysis or impact of the cantilever beam. For example, if I try to vary the length of the cantilever beam, affects the deflection, amount of deflection. The As you increase the length of the cantilever beam, the deflection increases. In turn, it affects the sensitivity of the device. Width of the cantilever beam impacts the stiffness. When you talk about stiffness is related to the flexibility of the material. If I apply 1 pascal of pressure, how how much my device is capable of deflecting. That deflection depends on the flexibility of the material. And flexibility of material we can understand through Hooke's law. I hope Hooke's law is familiar to us. Hooke's law states that the stress is equal to Young's modulus of that material into the strain created in that for that material. So Young's modulus decides the flexibility of the material. So if you want to make your material more stiffer, that is, if you doesn't want your material to be too much flexible, then you have to increase the stiffness. If you want to make it very flexible, then you have to decrease the stiffness. So impact of stiffness is observed while optimizing the width of the cantilever beam, right? And also thickness contributes towards the optimization of stiffness. But one thing we have to keep in mind is the more the stiff the material is, the sensitivity is lesser, right? Because in our analogy, as the cantilever beam deflects, the stiffness vary. The sensitivity of the material is directly proportional to the deflection of the cantilever beam. So we should make sure that our material is as flexible as, or flexibility is proportional to the applied pressure, right? So with this knowledge, we just let's see what happens when one end of the cantilever beam is fixed. The other end is free to move. As I said, there is a stress created across the cantilever beam because of the fixed constraint. So on the outer surface of the cantilever beam, as we all know, there are two types of stresses: tensile stress, that is longitudinal stress, and compressive stress. The outer surface of the cantilever beam will have experiencing tensile stress, whereas the inward face of your cantilever beam will be compressive. So when I have to look into the region where both are equal, and that is the middle of your cantilever beam, the middle of the cantilever beam is called as neutral axis. What does neutral axis means? In this particular region, neither there will be tensile stress, nor there will be compressive stress. This particular region will be stress-free. Okay. So we understood. What did we understand? Cantilever beam, one end is fixed, other end is free to move. So there is a stress created across the body. Outer surface will have tensile stress, whereas inward surface will have compressive stress. But the region which is exactly middle to both upper and lower region of the cantilever beam will be stress free. Stress will be zero at this region, and this region is called as neutral axis. Understanding this concept is very important when we enter into the design part of MEMS cantilever beam. It is also called as neutral surface. So neutral surface is usually the thickness by 2, that is the middle portion of your cantilever beam. So we will understand how to design a MEMS cantilever beam. For that, I have taken a design consideration. I have considered my cantilever beam to have length equal to 1000 micrometer, width of cantilever to be 100 micrometer, and thickness of the cantilever to be uh, 10 micrometer. If we have to visualize it, then the cantilever beam, it is a rectangular shaped. It is rectangular shaped, right? One end of the cantilever beam will be fixed, and then the length of the cantilever beam is considered to be 1000 micrometer. The width of the cantilever beam is considered to be 100 micrometer, and the thickness of the cantilever beam is considered to be 10 micrometer. This is the design parameters that we are considering for cantilever beam. So in session 2, you were introduced to COMSOL multiphysics tool, and you were also been introduced to the various steps that can be used in the COMSOL tool to design a cantilever beam. I will once again recall all these steps. So once you click on the COMSOL multiphysics icon, your main page will be open. COMSOL's main page will be open. You have to double click on model wizard. Once you double click on model wizard, you have to, as you know, what is the dimension of your device, you have to select the dimension. For us, MEMS devices are always 3D. So we will go with the 3D option. Double click on 3D. After you select the dimension, now it is, we have to decide the physics. Physics tells us that what we are going to apply on the device and what is expected from the, as an outcome from the device. So physics helps us to decide the input and output of the device. For my cantilever beam, I'm going to fix one end of the cantilever beam and apply force or pressure on the top surface or on a point. Okay, so fixed constraint and force are totally mechanical, right? They are mechanical inputs. So what I require is I require a structural mechanics. Under structural mechanics, I will select a physics, which is solid mechanics. So solid mechanics will help me to fix my device at one end and apply force on the surface or on a point. So I will select the solid mechanics, click on add, click on add button. So once I click on add button, we can see that added physics interface included solid mechanics, right? So my model has physics, which is solid mechanics. If you want to add any other physics, you can add. Otherwise, you can proceed to steady. So under study, there are different studies as you have been introduced in the previous session. Initially, we will choose stationary study. Stationary study helps us in understanding the device at a stationary point of view in a static condition. Okay, so I will choose the study as stationary and click on done. So with this, I choose all the prerequisites required to design my MEMS cantilever beam. When I call it as MEMS cantilever beam, we know that it is its dimensions are in micrometer range. So the length unit needs to be changed. Default, the length unit in your COMSOL will be in meter. So we need to change it to micrometer when it comes to MEMS design. After we do this, we have to first create the geometry. Our geometry is a rectangular shaped device with all these design parameters. So I go to geometry, right click and select block because my device shape is rectangular, right? So in COMSOL, width represents the length of the beam. So the length of the beam, I considered it to be 1000 micrometer. Depth is equivalent to the thickness of the material, which is 10 micrometer, and height is equal to the width that we are talking about in our device, which is 100 micrometer. Okay, so you have to feed in all the dimensions that you have considered for your device, and then you have to select build all object. So once you click on build all object, your device of a particular dimension and shape will be displaying on the screen. So I have modeled a MEMS cantilever beam. So now what I have to do is, after I apply all the dimensions, which is length, width, and thickness, in the design consideration, I have considered it to be a silicon cantilever beam. So I have to apply material of silicon, right? So my cantilever beam is of silicon, right? So to do that, what I will do, I'll go to the option called materials, right click on material, and there will be an option called add material from library. Okay, if usually all the materials that are required to design our MEMS devices are listed in the library, so we need not worry about much about the materials. So we can directly go to add material from library. If I click on it, towards my right side, the option for adding the material pops up. I have to choose silicon material. For that, first choose MEMS, and under MEMS there is an option called semiconductor. Select semiconductor, and under semiconductor there are two types of silicon. One is isotropic, another is anisotropic. So select isotropic and right click on the silicon, and then click on add to component 1. Why component 1? Because the main function of your model is named as component 1. Okay, so I'll repeat once again. You will right click on materials. You will select add material from library. Towards the right, you will get the list of materials from the library that is saved in the library of COMSOL Multiphysics tool. For choosing silicon, go to MEMS, semiconductor, choose silicon isotropic, right click, click on the option of add to component 1. So once you do that, if we see that, if we see here, all the material properties required for silicon material is automatically fed into the library. To design a MEMS cantilever beam or a material to be flexible, to move freely on the application of pressure or force, the three parameters that are very important for that particular material is density, Young's modulus, and Poisson's ratio, right? So the density value of silicon is fed, Young's modulus, Poisson's ratio, the parameters are already fed into the system library, right? So you can directly use a silicon, and then if you don't apply the material, the object will be in the gray color shade. Okay, so how to differentiate whether you have applied the material or not is that if the object, even after you choose the material, if the object is gray in color, that means you have not applied the material to the object. If you select the object, it becomes bluish in color, right? And the selection list will have the domain that is being applied with the silicon material. This gives you a confidence that you have applied the material to the model. Okay, so with this, we will proceed with the design first. I stop the simulation learning for now, and we'll first understand what are the design parameters required, and then we will again come back to the simulation. So having said that, we understood what is the dimension of the cantilever beam required. We understood what is the material. Based on the material, we will know what is the Young's modulus of the material. We will know what is the density of the material, right? If we go back to COMSOL, Young's modulus of silicon is 170 gigapascal and density is 2329 kg per meter cube. The same value is being utilized to proceed to the design. And I have considered to apply a force of 1 Newton, okay, at the free end. So with this basic knowledge, the first design equation that we have to understand is when we have a cantilever beam that is fixed at one end and you apply a point force, that means you're not applying the force on the entire body or entire surface of the cantilever beam, but you are applying a force on a single point at the tip of the cantilever beam. Then what is the maximum deflection the cantilever beam can take is governed by the equation here. Delta is the maximum deflection a cantilever beam can take, is given as F. F is the force applied at the point. L is the length of the cantilever beam. FL cube is the numerator divided by 3 into E is the Young's modulus. Depending on the material, we will know what is the Young's modulus of that particular material. And then I. What is I? We need to understand what is I. Okay, so I is area moment of inertia. So as I told, there is a neutral axis, right? There is a neutral axis in your cantilever beam, which restricts the bending of the cantilever beam. So this neutral axis is experienced by the cross section of your cantilever beam. So if I draw this particular cross section, it will look something like this, right? Okay. Now, this particular cross section restricts the bending of the cantilever beam. That is why it is called as area moment of inertia, and it is represented by symbol I. Suppose if I consider label the width as W and the thickness as T, then I will be equal to width into thickness cube, T cube divided by 12. Okay. So area of movement of inertia is the cross section area of our cantilever beam where the bending stress is very less or it is zero. Okay. Bending stress is zero. The cross section area is W into T, but thickness affects the restriction much more. That's why it is given as T cube by 12. So I is equal to W T cube by 12. And it is a very important parameter when we analyze the displacement of the tip, right? Because I is restricting the bending. So we need to understand how much the restriction is happening with respect to the width and the thickness. That is the cross-section area of the material. So delta is equal to FL cube by 3EI. And we know I is equal to WT cube by 12. Having known this, when we try to theoretically calculate, we know that delta max, that is the deflection of the beam, is equal to F, that is the applied force, FL cube by 3 into Young's modulus into I, right? So first we need to calculate what is WT cube by 12. So the width of the cantilever beam is considered to be 100 micrometer, that is 100 into 10 power minus 6, okay, into the thickness is 10 micrometer, 10 into 10 power minus 6, the whole cube divided by 12. So if you calculate, you will get your inertia in as 8.34. You can use your calculators to cross verify the answer. You will get it around 8.34 into 10 power minus 21 meter power 4. Okay. Unit is meter power 4 of your inertia. If you use this value in the deflection formula, applied force according to our design, I'm going to use 1 Newton of force. Okay, I'm applying 1 Newton of force in a point at the tip. So 1 Newton into uh, L is the length of the cantilever beam, which is 1000 micrometer. So 1000 into 10 power minus 6 power 3 divided by 3 into Young's modulus for silicon is 170 gigapascal. So 170 into 10 power 9 into the inertia that has been calculated, which is 8.34 into 10 power minus 21. So if you calculate this particular values, you will get the maximum deflection of 236.10610 millimeter. That means for this dimension of cantilever beam, when you apply a force of 1 Newton at the tip of your cantilever beam, the cantilever beam deflects for 235 millimeter, okay, from the origin. So let's check this. Any doubt here? All are following?
No doubts, ma'am. It's clear.
Okay. Thank you. Thank you. So keeping this. Sorry? Please kindly mute yourself. So keeping this design parameter in the mind, so already we have added silicon material. We have designed our cantilever beam. Now what is required is we need to fix one end of the cantilever beam and apply a point load in the other end. Okay. So that has been done using our physics that we added in the earlier stage of our simulation, that is the solid mechanics physics. Okay, so right click on solid mechanics. You will find an option called fixed constraint. Choose the fixed constraint option. Choose one end of the cantilever beam. The bluish color will indicate that the surface is being selected and it is being fixed. Okay, and then you need to now apply a load in the other end of the cantilever beam. It is a point load. So I will right click on solid mechanics. You will have an option called edges. Edges, if you just keep your mouse on the edges option, you will find the edge load. Okay. So the edge load will allow you to apply the load on the edge. Okay. So there is a difference. Cantilever beam will have experienced different loads. Either it is a point load or a distributed load. For now, we will just understand the edge load or the point load. So now I am going to apply this particular load in the load type is force. That means I'm applying force at the tip, and then it will be in the y direction. Okay, because the cantilever beam deflects in y direction, the load I have applied of 1 Newton in the y direction. So I have fixed my cantilever beam and I have applied the load of force in y direction of 1 Newton on the other end, with the end that is free to move. Okay. So now what I have to do, I have to mesh the device. So I will click on the mesh, build all. My device is meshed. COMSOL multiphysics tool is a FEM tool, that is finite element modeling tool. So here meshing is very much required because all the governing equations will be applied to your device in a minute model. Okay, your device will be divided into smaller modules, and all the equations will be applied on the minor modules, and then the average of the result will be displayed to you, which marks the accuracy of the result. Okay, so now after meshing the model, click on study one and select compute. So once you select compute, the default result that will be displayed to us is the stress. One Mrs. Stress means the average stress the body takes. Okay. So this end of your cantilever beam is fixed. So the stress is maximum at the fixed end, whereas the stress is very minimum. That is, the maximum stress is 5 into 10 power 11 Newton per meter square, whereas the minimum stress is 1 into 10 power 11. So the free end is having a very minimum stress. To understand how much the cantilever beam is deflected, you have to go to results, right click, select 3D plot group, okay, and then again right click on 3D plot group, select surface, okay, and then click on plot. So once you click on plot, you will get the maximum deflection of the cantilever beam for the applied force of 1 Newton in your Y direction. So if you see here, it is 2 power 2 into 10 power 5 into micrometer, which is very much near to the design that we have done. With simulation result, we are getting 200 millimeter. If you convert 10 power 5 into 1 micrometer, you will get the value around 200 millimeter, and the theoretical value is 235, which is very much matching with the design, right? So this is how you design your MEMS cantilever beam for a particular deflection. If you want your cantilever beam to deflect 1 millimeter, okay, for the force of 1 meter, then you can keep one parameter as unknown. Other parameters can be assumed, and you can calculate the length of the cantilever beam, or you can calculate the width of the cantilever beam. Thickness of the cantilever beam cannot be varied because it will be foundry decided thickness, right? We are going with process flow. So thickness cannot be varied. Thickness will be, information will be considered from the foundry that we are going through, process flow that we are going through. So either we can modify or assume width and calculate what should be the length for a particular deflection, or we can assume the length and calculate what is the width required, right? So this is one of the design parameter for MEMS cantilever beam. Next, we need to understand the stiffness of the cantilever beam. Why stiffness of the cantilever beam should be understood is, most of the cantilever beams will be designed for a particular resonant frequency. What is resonant frequency? It is the frequency at which your cantilever beam can oscillate. Okay, so many applications are based on the resonant frequency. For example, if you take a hearing aid application, our ear can have a listen to a voice around 4 kilohertz. Okay, the audible frequency, speech frequency is around 4 kilohertz. So if you want your diaphragm to have maximum sensitivity around 4 kilohertz, then you have to design your device to resonate at 4 kilohertz. That means it is giving the maximum displacement at that particular frequency. Okay, that is the in short understanding of resonant frequency. And resonant frequency is usually dependent on the stiffness of the material and the mass of the material. Okay, so F is given as FR, which is the resonant frequency of the device, 1 by 2 pi root of K by M. K is the stiffness of the material and M is the mass of the material. So the stiffness of the material is calculated using the equation K is equal to 3 EI by L cube. Again, E is the Young's modulus of the material. I is the moment of inertia. L is the length of the length of the device. So if we calculate the stiffness of the if we try to calculate the stiffness of the material that we designed, so K is equal to 3 EI by L cube. So if I apply all the value, E is 170 gigapascal. We calculated it to be 8.34 into 10 power minus 21 divided by 1000 micrometer cube. Then the stiffness of this particular device, we are getting it around 4.25 uh, 2.53. Okay, and the unit of stiffness is Newton per meter. Okay, the unit of stiffness is Newton per meter. So what is resonant frequency given as? Fr is equal to 1 by 2 pi root of K by M effective. M effective is the effective mass, because we know that cantilever beam is fixed at one end and not all the body of the cantilever beam bends for the applied pressure, right? There is a effective mass. There is a effective mass that only is deflected, whereas the other part of the body is constrained to move. So effective mass gives us the mass that is actually deflecting. Okay, and the effective mass M effective is given as 0.24 into the density of the material. So in the console, we add the information about the density of the silicon. We can use the same value, density of the material, because we know that mass is equal to volume into density, right? Volume into density. For a rectangle, the volume is length into breadth into width, right? Length into width into thickness, and the density is symbolized in this manner. When you call it as an effective mask, it is only the mass that is deflecting. So the effective mask is being multiplied by the value of 0.24. Okay, so this is the effective mass of your, this is how you calculate the effective mass of your cantilever beam. So once you calculate the effective mass of your cantilever beam, for this particular cantilever beam dimension, I'm getting the effective mass as 5.5. Okay, 5.59 into 10 power minus 7 gram. Okay, 10 power minus 7. It will be kg per meter cube. Okay, kg, not meter, it will be only kg. It is mass. So 5.59 into 10 power minus 7 kg. And if I have already calculated my stiffness. So when I apply to the resonant frequency, the value of stiffness and the value of mass, the resonant frequency that I get is around, the resonant frequency that I get is around 13,800 hertz. Okay, you can calculate the value and cross verify this particular value. So the resonant frequency is around 13,800. Now, if I want to understand whether my design is correct, whether I have designed my particular cantilever beam for 13,800, then what I have to do? I have to go back to console tool. Now the steady will not be stationary. I have to add a new steady, right? So if I I have to add a new study. So what I have to do, I have to go to my toolbar. There will be an option called study. Okay, click on the option of study. And then third option will be add study. I have to add a new study because stationary will not give me the frequency analysis. Okay, I have to add a new study which gives me the frequency analysis. Okay, to do that, what we do, we go to the toolbar, select study, select the third option, which is add study, and now you have to select option called eigenfrequency. Okay, eigenfrequency is the study which gives us the information about the resonant frequency of our device that is being designed. Okay, so you have to right click on the eigenfrequency, select add study. Once you select add study, towards your left in the setting window, model builder window, you can see that steady 2 is been added. And what is the steady? It is your eigen frequency. Once you add the steady, select compute. So once you compute your model for eigenfrequency. Can you see here? This is the eigenfrequency. That is the first mode of resonance. Usually the devices will have 6 modes of resonance. But usually first mode of resonance is required for designing any device. So the first mode of resonance is around 13,893 hertz. Okay, which is very close to the design that we have done. We have designed our device for resonating at 13,800 hertz, and through simulation we are getting the same resonance. That means the length of 1000 micrometer, width of 100 micrometer, and thickness of 10 micrometer resonates at a frequency of 13,800 hertz. I hope it is very clear to you all, the design parameters. Can we proceed?
Yes, ma'am.
Yeah, thank you. So we have understood about the deflection of the cantilever beam. We have understood about the stiffness, resonant frequency, and then we can also find out what is the maximum bending stress, that is sigma max, that is occurring at the fixed end of your beam. It is provided by 6 into F is the applied force, L is the length of the cantilever beam, by W into T square. When you calculate this, you will get around 8 into 10 power 11 Newton per meter square, and through simulation you are getting the stress around 5 into 10 power 11 Newton per meter square. You can cross verify the same, but the equation for calculating the stress, maximum stress at the fixed end, is this particular equation. Okay, so I also want you all to learn how to plot frequency versus displacement. To plot frequency versus displacement, first you have to understand what is the resonant frequency. So you have to compute the eigenfrequency study. After you compute eigenfrequency study, you have to add one more study which is called as frequency domain. Okay, you can right click on frequency domain, click on add study. This domain allows you to set the range of frequency for the device to understand the resonance. Okay, so once you add the frequency domain, there will be a range window where you can add the starting and ending frequency that you want to analyze for the cantilever beam. Since from the eigen frequency, I understand that 13,800 is the resonance frequency for my cantilever beam. So what I will do, I will start from 1000 hertz at a step of 2000, and I will stop the analysis at 15,000 because I need a window in which between which the resonance falls. Okay, so I'm starting from 1000. I'm stepping forward by 2000 hertz, and the last frequency is of 15 kilohertz, okay, or 15,000 hertz. So I add the frequency, I add the range, and I click on compute. So it is computing for the displacement is being computed for all the frequencies that is being arranged in the frequency domain. So to plot it, go to results, right click, select 1D plot group. Okay. Right click on 1D plot group, choose point graph. Okay. If you choose point graph, you have to choose a point where the displacement is maximum. So if you go back to the surface 3D plot group, you will understand which end of your cantilever beam is deflecting more. The red color indicates the maximum deflection. So come back to your point graph. You have to select the data set to be steady 3 because steady 3 is what is your frequency domain. And then you have to select the point, any one point you can select which is experiencing maximum deflection. Okay. So y-axis you will be plotting displacement. X-axis will be the parameter value, the value that is being decided by you in the frequency domain steady. Okay. After this you can click on plot. Right? So this is your frequency versus displacement plot for your cantilever beam that you have designed. Okay. So for a frequency from 0 to 0 to 8 kilohertz, the displacement is very minimal. After 8 kilohertz, the cantilever beam is trying to displace a little bit, but once it reaches around 13,500, the displacement is maximum. After that, again, the displacement decreases. So the maximum displacement or the resonant frequency of your cantilever beam is the 13,800 hertz. And this is how we design MEMS cantilever beam with design aspect. I hope the understanding was better. You understood how to design a MEMS cantilever beam. Any queries can be asked. So I hope you have learned how to design and simulate a MEMS cantilever beam.
Yes.
Excuse me, ma'am.
Yes, sir.
Ma'am, I have joined in the middle only.
Okay.
Extremely sorry. What about the dimensions, madam? 1,000 meters the length?
Yes, sir.
1,000
I'll
mm.
share my
Oh,
screen
yeah,
again.
yeah.
I just wanted to tell you all that there is a quiz and feedback. Please do not leave the teams. I have to share the quiz and feedback link. I'll just answer sir's question and come back. Is the screen visible, sir?
Yes, ma'am.
Yes, sir.
Yes.
Yeah, I have taken length to be
Okay.
1000 micrometer, width to be 100 micrometer, and thickness to be 10 micrometer.
Just a minute, ma'am.
So usually what we'll do, we will be designing the cantilever beam for a particular frequency. Okay, so resonant frequency plays a very important role for designing the cantilever beam for a particular application. In that case, what we have to do, the thickness of the material will be already fixed by the process flow. The overall area of the area, that is length into width, will be fixed by the process flow. But within the area, what should be the length of the cantilever beam and width of the cantilever beam can be decided by the resonant frequency that we are designing. So resonant frequency, we know it is 1 by 2 pi root of k by m. Either you fix k or you fix m, and based on the assumption, you can decide what should be the length and width of a cantilever beam for a particular resonant frequency. This is how we do the design.
What about the material, madam?
So material will be decided by the process flow itself. For example,
Okay.
now we are going with SOI standard process flow. There the material is silicon. Your device material will be silicon.
Okay.
So
Here what material you have selected, madam?
I have selected silicon itself. Sir.
Silicon. Okay.
Yes.
That's all, madam.
Okay, thank you, sir. Any further queries?
Ma'am, I have a question.
Please, sir.
The question here is the soy process flow is a standard thing for all MEMS, or is it having any specific to
No,
those which are
no.
going to be used in biocompatible conditions?
No, sir. Soy MEMS is not, it is just a process flow. Okay. So if you want a single layer, if your device is having only single layer, then you can go for soy MEMS. If you have multiple layers, then there will be different processes. But to understand the initial MEMS design, we are going with soy MEMS. So it is not that soy MEMS is the only process or it is the only method to fabricate the device.
Yeah, thank you.
Yes. So I'm posting the Google form for quiz. We have created a WhatsApp group. I have shared the link through mail. I request all of you to join the WhatsApp group for any immediate communication. And I also wanted to inform you all that due to commitments in our college, this Saturday we are unable to schedule the training program. Instead, we are going to reschedule it to Tuesday. So I require a kind support from all the participants. Instead of Saturday slot, I'm going to schedule it on Tuesday. Is that fine with all?
Looks fine, ma'am.
Yeah, thank you, sir. There is an unavoidable situation in the college, so we are unable to proceed with the training on Saturday. But the same session will be carried out in the Tuesday slot. I will be sharing the session link and email regarding the same. I have shared the Google form for feedback and quiz. I kindly request all of you to please fill both the forms, which marks your attendance, and we also have to know how much we are able to deliver. So I had created a quiz and feedback. WhatsApp group link, I will share it here again so that it's easy for us to join. I hope all are able to download the console tool from iSTEM.
No, I'm not able to. I mean, not yet, ma'am. I think.
Yeah,
today or
sir.
tomorrow.
Actually, what happens is iSTEM, when you register, after registration, they take some time to approve your registration.
Okay.
Only after your registration approval, you will be able to
Apply
download
for
it.
this.
Yeah,
Apply for
yeah.
this. Then
Yes, sir.
So the registration has got approved and I've applied for the same. I think then
Oh.
again, next level of approval is required, maybe.
Oh, great, sir. Great.
Thank you.
I hope all are able to access the Google form for both quiz and feedback. So, dear participants, it was very good to again meet you all and share a few knowledge that we have gained in our experience. So thank you all for joining the meet, and we will be meeting you all again on next Tuesday. The session will be on how to design a capacitive sensing MEMS devices. Okay, because SOI standard process allows us to develop only capacitive sensing mechanism. So we will be understanding how to design and simulate MEMS based sensors using capacitive sensing mechanism. With this, I take a leave, signing off. Thank you all.
Thank you so much, ma'am. Thanks a lot. Indeed, very useful.
Thank you. Thank you, sir. Thank you. Thank you.